Hi everyone, thanks for joining us today for the 2 Degrees C Climate Chat. Joining me today again, Dr. Carsten Shine, and our guest today, Dr. Jennifer Jackson of the Hakai Institute in Canada, here to discuss her work as a physical oceanographer in British Columbia. Her work focuses on how the ocean is changing and the ripple effects that are manifesting throughout the ocean realm. So join us as we explore in the 2 Degrees C Climate Chat. Okay, guys, joining us today again, like I said, Dr. Carsten Shine and Dr. Jennifer Jackson from the Hakai Institute in British Columbia, Canada. Welcome to both of you.
Thank you for having me.
Thanks. So, Carsten, I wanted to frame this discussion a little bit. There's quite a lot in the news cycle about the Arctic and warming that's occurring in the Arctic. Maybe you can help the listeners understand a little bit about why this particular discussion is important.
Certainly. There are a few places really where the effects of climate change have been as acutely felt as in the high latitudes. Historically, climate observations across the Arctic have shown warming that's much greater than we've seen anywhere else. Nearly all the climate models out there are in agreement that the region will continue to warm much faster and to a greater degree than lower latitudes. This is really bad news for both Arctic wildlife and Arctic communities. Things like changing ocean chemistry and temperatures are changing fisheries production, decreasing it. Longer periods of open water are accelerating shoreline erosions, threatening a lot of the native coastal communities. Permafrost throughout the region is thawing more deeply, causing roads and buildings to destabilize. In fact, just last summer, thawed permafrost caused the collapse of a large fuel tank in Siberia that dumped over about, I think, 20,000 liters of diesel fuel into a nearby river. And this is really what makes the work of those such as Dr. Jackson so critical.
Good. Thank you. So, Jennifer, welcome to the 2 Degrees C Climate Chat podcast. I know we've had the discussion to bring you in a couple of times, so we're happy to have you. I wanted to get you to perhaps introduce yourself to the listeners and so that they can understand who you are and what you're doing up in Canada.
Sure. Yeah. So I am a coastal physical oceanographer, and a physical oceanographer basically means I study the physics of the ocean. And my main focus has been ocean climates, largely changes in temperature, but also changes in oxygen as well. And at the Hakai Institute, we study the coastal margin of British Columbia, which we sort of define as everything between, well, the glaciers actually, right to sort of the edge of the continental shelf. And so some of the main foci there have been looking at long-term time series in some of the different inlets and fjords in British Columbia.
Awesome. So, the Hakai Institute, like you say, it's specifically coastal work in British Columbia. So, what kind of climatic changes are you seeing, and what warning signs can we expect that are being shown there?
Yeah, so I mean, I like to think of the major climate changers in the ocean. There's three big ones. The first is temperature, so the warming of the ocean. The second is deoxygenation, or the loss of oxygen in the ocean. And the third is ocean acidification. And all three of those are somehow sort of interconnected, but also together they change the physical environment of the ocean, and that has profound impacts on the ecosystem as well. I'd like to also say sort of the big four that I like to think about is also the increase of plastics in the ocean as well. It's not necessarily a climate change indicator, but it's, the fourth large, change that we're seeing in the ocean.
Right. And being an oceanographer, you're watching some of that, in the sampling that you're doing. But as far as I understand, your main study is related to ocean heat. Is that correct?
Yeah, that's right. Yeah, and so for British Columbia in particular, we've amalgamated about a 70-year long time series, which is quite amazing for some coastal waters. There's not a lot of time series that are that long. They started in 1951 with a professor named George Picard, who was at the University of British Columbia, and he did these inlets cruises into the different fjords or inlets around Vancouver Island and British Columbia. There's about 85 different inlets across British Columbia. And so he amalgamated over his 30-year career this amazing time series that more or less ended in the 1980s. There were a few different sampling events after that, but there were large data gaps between about the 1980s and the early 2000s. And then the Hakai Institute, which is funded by the Tula Foundation, started sampling in the region in around 2008. And we had the ability, because of where our field stations are, to collect year-round high-resolution data, and from which we could resolve the seasonal cycle, which is really important when you're thinking about long time series. Is you have to be able to look at the trend over decades instead of just the trend over a seasonal cycle. So you have to know what the seasonal cycle looks like. And because we've been able to have time series over the last 10 to 15 years, we could really sort of fill in what's been happening since the 1950s. And what we're seeing, and I've been really focusing on inlets, in particular 4 different inlets, Rivers Inlet, Knight Inlet, Butte Inlet, and Douglas Channel, which is farther north, and that's in collaboration with Fisheries and Oceans Canada. And what we're seeing is it's actually deep water that's changing the most. And deep water is everything that we define as below the sill of these inlets. So these inlets were essentially carved out by glaciers as glaciers have or during the last glacial maximum. And then as the glaciers retreated, they left an ocean behind. And at the head of the glacier, so where the glacier ended, they've left a sill behind. And so sometimes the sills are only tens of meters deep, sometimes they're hundreds of meters deep. But they almost act as a barrier between the rest of the inlet, which can often be up to 700 or 800 meters deep. And so what we've found is that the water that is deeper than the sill depth in these inlets is actually changing, and it's changing about twice as fast. It's warming about twice as fast as waters of similar depth in the open ocean. So it's stark changes, and it's changes that are almost similar to the type of changes that we're seeing in the Arctic. And it's making us think that these inlets are really a hot spot for climate change.
That is interesting. And just sticking with that thought for a second, are you noticing specific changes that are occurring in migration of species and things like that?
Yeah, so a lot of the work that we do, we work very closely with the coastal First Nations in the area, particularly the Heiltsuk and the Wikinuve and the Homalco First Nations, and they're really interested and alarmed by the disappearance of salmon. We've had, most salmon along the coast have really crashed in the last decade or so. And what we think, one of the reasons we think the salmon are crashing is that where British Columbia lies, it's a junction between sort of colder, more subarctic waters and warmer, more subtropical waters. And depending on how the winds and the climate shifts, you can get either more southerly, warm waters into British Columbia or more northerly cold waters into British Columbia. And when you bring the southerly warm waters in, you also bring the zooplankton. And the southerly zooplankton are a lot less nutritious than the northerly zooplankton. The northerly species, they have lots of fat, lots of lipid. And so when a juvenile salmon comes out of a stream and eats one of those zooplankton, it's good for the salmon. It gets lots of fat, it grows quickly. And so as it continues out into the open ocean, it's in quite good shape to survive the years until it has to return to spawn. But when a juvenile salmon comes out of the stream and it has one of these sort of less nutritious, almost junk food-like southern copepod species, it needs to eat a lot more of them in order to grow and to build the fat stores that it needs. So that's one of the reasons we're thinking that the salmon just aren't doing that well, is because these warm waters have sort of shifted in, brought with them these southerly species. And so just the marine ecosystem is not as conducive to salmon growth as it would be otherwise.
And of course, that has a trickle-on effect throughout the food web because salmon obviously not just ecologically important or economically important for humans, but they're ecologically important for other species. So,
Absolutely.
and Carson, I mean, we're seeing quite a lot of that right now. Just sticking with salmon for a second, in the US, that's made quite a bit of recent history in the news, and that surely is related to the climatic conditions that are occurring on the western half of the United States.
Oh, that's absolutely right. In down in California, I believe they're trucking. They're literally trucking something like 17 million salmon to the ocean because there's not enough flow in the rivers right now because of the ongoing drought out there. And up in Oregon, there are talks about diverting irrigation water away from farms to ensure there's enough flow for salmon to make it to the ocean, and that's got a lot of the farmers very anxious about what may happen there.
And that relates back to the change in precipitation. I'm assuming.
Yeah, the ongoing mega drought that's going on right now in the western United States, especially in the California region, Oregon region, where they have not had normal precipitation in quite some time.
And again, that relates back to snowfall as well, correct?
Correct. A large amount of the drought depends on, or ameliorating the drought would depend on having a decent snowpack in the winter for it to melt off gradually during the spring and supply a lot of those streams with the water they need and the groundwater recharge that farmers might need to plant their crops and defer irrigation until later on in the summer.
Described barefoot luxury, the casually sophisticated Southern Cross Club is Little Cayman's original resort. This hidden gem is as unique and vibrant as the island it inhabits. A true island treasure, it is the perfect place to dive, fish, and relax. Its 14 beachfront bungalows are situated on 900 feet of white sand, only minutes from the world-class diving found only in Little Cayman. Visit www.southerncrossclub.com to book your escape to tranquility.
Hi, I'm Adrienne with Quest Dive Adventures, and you're listening to the 2 Degrees C Climate Chat podcast.
So, Jennifer, you've spent a lot of time up in the Arctic Circle.
Yeah.
I mean, you live fairly close to it, but you're not quite there. But you have spent quite a bit of time up there, mostly on ships, I'm assuming?
Yeah, that's right. So during my PhD, I had 2 cruises in the Canada basin of the Arctic Ocean, which is the water that's directly north of sort of Alaska and Yukon. And we went as far north as 80 degrees on those trips. Yeah, and each trip was about 5 to 6 weeks long. I found out I was pregnant with my son on the second
wow.
trip. That was a big surprise. So I haven't been back since. That was an interesting cruise, but it's not necessarily conducive to having being a woman with a young family or these Arctic trips. So unfortunately, I haven't been back since 2007, but I spent about a decade studying Arctic ocean conditions.
So, looking at your studies there, based on the knowledge you learned then, and looking at the conditions now, what can you see is changing based on your experience?
Yeah, I mean, the Arctic is so interesting and it's so complicated. And part of the reason it's so complicated is that it's influenced by all the other oceans in a way that most other water bodies aren't. So, if we consider the Arctic almost as different layers, the deepest is water that sits there for thousands of years, and it's Arctic deep water, we call it. Above that is a layer that's about 1,000 meters thick that's largely composed of Atlantic water flowing in, and it flows in through the Barents Sea and Fram Strait. Above that is a layer of water that's about 150 meters thick, and it's water that flows in from the Pacific Ocean through the Bering Strait. And then above that, you have water that's sort of seasonally influenced by Arctic processes. So it's the true Arctic surface water. And that layer in itself is really complicated because it's influenced by both sea ice formation and sea ice melts. There's large rivers that flow into the Arctic, and those also contribute to what we see in the surface waters. Um, and all of these different layers are changing. For example, the Pacific waters are warming. There was a big influence of the marine heat wave. So the water that's been flowing in through the Bering Strait and the Bering Sea, that's been really warm, and it's been warm enough that it's melting sea ice along its path, which it never used to do. The water that's been moving in from the Atlantic has also been changing, and you can see huge amounts of seasonality and different decadal and interdecadal oscillations even within the Atlantic water. And then the deep water, it's quite stagnant. So it just sort of sits there and it doesn't change very much yet, though I imagine the change is yet to come. And so the Arctic is interesting in that sense, is that it's not just processes that happen within the Arctic that cause that body of water to change, but it's processes that happen sometimes, thousands or even tens of thousands of kilometers away that really influence what's happening in the Arctic. So it's largely been changes, again, to heat. It's been warming rapidly. The sea ice has been melting rapidly. When the sea ice melts, it leaves this really fresh or buoyant layer on top of the ocean that then influences how the ocean interacts with the atmosphere and how sea ice is formed. So it's really complicated, but big changes that we're seeing there.
And if we relate this back to our primary concern in this, right now, is certainly climate change and the amount of carbon dioxide that is being absorbed by the oceans. And Carsten has told us quite a few times on the show about how the role of the oceans, or the importance of the ocean in the uptake and sequestration of carbon. But if you look as an oceanographer, if you look at those layers of water, are they affected much by the heat, by the amount of carbon dioxide that they're able to sequester?
Yeah, and certainly, again, they each have their own signature. And like the Pacific water, for example, is quite acidic, and much more acidic than other bodies of water that you see in the Arctic. So where the Pacific layer sort of ends up depends on its density as it flows in. So if it's warmer, it's going to be lighter, and that means it's going to sit closer to the surface where a lot of the animals that we care about are going to be influenced by that more acidic water. And of course, the Pacific is continuing to be more acidic. The Pacific is sort of the end of what we consider this great conveyor belt that takes up thousands of years, where water is sort of formed in the North Atlantic and in the southern Atlantic Ocean. And then it takes time, it sort of sinks and moves around the world's oceans. And the end of that big conveyor belt, and again, it takes, in the order of thousands of years, is the North Pacific Ocean. And so the water that's there, it's acidic, it's got really low oxygen. And eventually, sometimes that water sort of comes towards the surface in places like the Bering Sea.
Right, and and this actually leads to my next question, because we had if we look at the way that your studies are performed, you're doing research from sensor data, but you're also using bottle data, and I'm assuming what do you see in the bottle data?
Yeah, so I mean, most of our sensor data now, we can look at most of our physical properties using sensors. So again, temperature, how salty the water is, what the density of the water is, how much oxygen in the water. That largely can be done by sensors. But most of the biological variables that we study, you need bottle data still to look at it. So for Hakai, for example, our studies around British Columbia, we sample through bottles and nets, sort of everything in the lower end of the food chain. So we measure viruses, we measure bacteria, phytoplankton, which are the single-celled plants in the water, zooplankton, which again are those like little kind of bugs or crustaceans often that we see. And so from that, we can sort of determine what's happening to the different levels of the food web. We also measure nutrients as well, because the phytoplankton, what grows depends on the ratio of different nutrients that we see. And that really is the very base of our food web. So the studies are preliminary. We don't have the same time series in the different components of the ecosystem that we do in, say, temperature, oxygen, or salinity. But we can start, patterns are emerging. So one of the ones that I mentioned again is sort of the invasion of the southern zooplankton species. Um, another big change we're seeing is the nutrient ratios, which again are sort of the base of what phytoplankton can grow. Those changed considerably during the marine heat wave in the North Pacific from 2014 to 2016. And so, again, we don't always have the data of the phytoplankton to see what changed, but we imagine that the different species that we're seeing is going to be quite different. And same with viruses and bacteria.
Right. Wow, that is interesting. Carson, I wanted to stick with the Arctic for a second. There are a couple of terms that pop up in the news cycle quite a bit. And, one is Arctic amplification, and the other one is climate pushing. Can you perhaps help us understand a bit what's going on there?
Sure. So some of the concerns really are that in addition to things like the surface ocean circulations pumping a lot more heat into the Arctic region, the atmosphere itself is trapping a lot more heat than it used to. In fact, a recent NOAA and NASA study that just came out suggests that the Earth's atmosphere is trapping about twice as much heat as the models had anticipated at this time. So that does not bode well for future temperature increases, especially in places like the Arctic. But in turn, all of this additional heat is altering patterns of the jet stream, for example, forcing it farther north in the summertime, bringing storms up to those regions that didn't used to get summertime storms, and not as far south in the wintertime. So on top of that, snowpack is in many places decreasing and is even disappearing in the summertime, and that's altering the feedback with air temperature. Generally, more snow equals more reflection, and which equals decreases in air temperature. But with the absence of snow and ice, more solar energy gets absorbed, and that further heats the surface and melts more snow.
Mm-hmm. Yeah. So, and the same would be true of the ocean as well. The sea ice would then protect the sea temperature below.
Exactly.
Is that correct? Yeah.
Yeah, exactly. I mean, the sea ice has a very high reflectivity, but the open ocean has a very low reflectivity. It absorbs a lot of what it receives.
Yeah, and sticking with that, Jennifer, I see a lot is written about the Laptev Sea and the sea ice occurrence in the Laptev Sea, and been tracked for a long time. Are you seeing similar changes on the northwest coast of Canada?
Yeah, absolutely. I mean, I was on the ship in 2006 and then again in 2007. In 2006, we think of as like the last year when there was multi-year ice in the Canada basin. And by the time we got there in 2007, it was largely gone. And it's really just first year ice that melts every year now in the summertime. So, the Arctic or the Canada basin of the Arctic Ocean is largely ice free now in the summertime, whereas it used to be fully covered with ice. And actually, during my PhD, I sort of studied that interaction quite intensively because we found that when you have that much sea ice melting, you actually leave this layer of really fresh water at the surface that essentially traps the heat below it.
Mm-hmm.
And so every year you get solar radiation that warms the ocean. And then now it used to just sort of release from the ocean in the autumn as you got mixing from storms and sea ice formation and that sort of thing. But now because there's this layer of sea ice melt that wasn't there before, it actually traps that heat into the ocean. And that heat is available to now melt ice during the winter time, which is another new process that we hadn't seen before. And it's possible as well that sort of, instead of the sudden loss of heat that we used to see, to this gradual loss of heat, that is also what's influencing some of the storm tracks and the changes in the atmospheric circulation that we see as well.
Wow. And that the loss of the sea ice in those areas, that's going to have quite a significant effect on particular species that make their life living on sea ice and below sea ice. Certain species of zooplankton and things like that. What can you tell us about what is happening local to that area? Obviously, the further north you go, you're looking to Arctic species like polar bears. But what have you seen as part of your studies? Not even just in the coastal area, but some of the areas that the Hakai Institute is following, where those changes are occurring.
Yeah, I mean, one Arctic example that's really stuck with me, and probably the most stark of an example that I can think of, is the northward migration of Pacific salmon. And so, for a couple decades now, they've been observing Pacific salmon in the Mackenzie River. And they've never seen that before. And we don't necessarily know what stocks are there. We don't know if they survive. We just know that there are Pacific salmon in the Mackenzie River now. So I feel like that's quite a stark northward migration that we haven't seen before. Um, for the BC coast, one of the largest changes that we've seen is the loss of sea stars, which we think is really impacting the marine ecosystem. We're part of quite a big study right now that's being led by Alyssa Gaiman from UBC. And she's been focusing on Pycnopodia, those big sunflower stars, which are
Mm-hmm.
now critically endangered.
Right.
And trying to understand, why we still see pockets of adult populations, and trying to understand under what conditions they can survive, and under what conditions they die.
Mm-hmm.
Again, everything is sort of pointing towards temperature, possibly oxygen is another stressor for these species. But they really are an important species for the nearshore environment. Even we think could be influencing things like kelp and other types of ecosystems that we know and love. And
Yeah.
so, yeah, that's been one of the major changes. We don't know if it's temperature, and that's still the jury's out as to whether it's a virus, or it was temperature stress itself. But I think, one thing I like to think about a lot is I know how stressful it is for humans when we're in a marine heat wave situation. And we have a much bigger temperature range that we can live in. I mean, we can live in minus 60 to plus 60 degrees if we have to, right? I mean, we have means of adapting to that.
Mm-hmm.
Whereas an animal in an ocean, it might be used to living in about a 5 degree Celsius temperature range. And if you're at sort of the top of that temperature range for long enough, the warmest that you can really tolerate, it's really going to cause cumulative stress. And so when there's things like viruses or bacteria or other things, you know, animals that want to eat you, you're not as fit as you would be otherwise. And these are concepts that we're just really starting to think about now, as sort of the cumulative stress of multiple years of not ideal conditions.
With so many wonderful destinations around the world to choose from, a little help can go a long way. Quest Dive Adventures is your premium adventure travel company, offering a wide and diverse selection of destinations to choose from, with dive adventures from the Pacific to the Caribbean and adventure travel from Costa Rica to Africa. Quest Dive Adventures offers packages including flights and accommodations, activities, transfers, diving, and more. Everything to enjoy your perfect vacation. What's your request? Yeah, yeah, definitely. If we look at the United Nations new Ocean Decade initiative, what priorities can we expect need to be actioned there?
Yeah, so I mean, I think again, it's reducing, unless we reduce our CO2, issues in the ocean are just going to continue. The things we're talking about aren't going to go away unless we start really drastically reducing our CO2 output. So that's, in my mind, the number one, achievable goal is that we meet our 2030 commitments, of our emission or of our CO2 emissions. I mean, that's absolutely critical. But I think there's another, there's the plastic problem, of course. That's another huge issue that really needs to be dealt with. But I think there's also a lot of societal issues as well. And, personally for me, I feel like equality in ocean science and ocean monitoring, not just in ocean science, but equality in the way that we use the ocean is also really important. I can speak to ocean science, I know it the best. And we still don't necessarily have a gender equality. We don't have equality from, different countries. We're still largely, you know, the wealthy nations have large ocean science programs because ocean
Hmm.
science is really expensive.
Yeah.
But that doesn't mean that, the hundreds of other nations that have coastlines aren't concerned and don't have necessarily a right to know what's happening in their waters as well. And so I really do think that this inequity needs to be addressed. And I also think that, again, I work closely with some really wonderful colleagues who are Indigenous, and I learned so much from their points of view. And it's been such a reminder for me to know we've got our Western science, but we have this parallel Indigenous science.
Hmm.
And there is so much knowledge in there. And, we've often thought that we should incorporate Indigenous science into Western science, but I really don't think that that's necessarily the way forward. I think we can use them in parallel and understand that they're equally important. And that, maybe we need to break down some of these barriers of what an ocean scientist is in order
Right.
to incorporate that knowledge into our world.
And that actually brings me to my next point because, as you said, you know, climate change does certainly affect indigenous people in different ways to people who live in urban environments. But this also means that they're on the forefront of the receiving end of the changes that are occurring. Um, are there opportunities in your local area or with the Hakai Institute where citizens can participate in citizen science efforts?
Yeah, absolutely. I mean, there's a few big citizen scientist programs. One's through the Pacific Salmon Foundation. They have essentially lent CTDs to different people to go out and collect the data, people that own boats. So that's been really wonderful. But again, CTDs are really expensive. I mean, they're like $30,000 or so. And, for some of the indigenous communities, that's just an insurmountable cost. And we're often asked of ways that we can, that they can collect their own data in a way that is feasible for them. So yes, I think any sort of, and a lot of the indigenous communities are out on the water and they know the water way better than I do. And so finding ways to equip them with instruments, I think, would be really helpful for all.
Yeah, and Carson, I know you and I are smiling because we've been working on this exact point for 5 years now. So
Exactly.
we will hopefully have an answer and to the CTD cost. But I wanted to also ask you, just staying with that the United Nations Ocean Decade Initiative, how can we build? Let's preface this. You previously mentioned that this is all one interconnected ocean. Doesn't matter where you live in the world. At some point in the spectrum of time, molecules of water will travel through the ocean conveyor belt and go everywhere around the world. So how can we build a better communication structure with regard to the ocean's role in climate change?
I think we need to engage as many people as possible, and we need to make most of the knowledge that scientists have and that other people have as well. We need to have as many voices in the conversation as we possibly can. People that anyone that's influenced by the ocean should be part of the conversation, in my opinion. And so, whether that's through media, whether that's through you know engaging specifically within different communities. I'm not sure necessarily how to go about doing it, but I really think this is an opportunity for everyone to be part of the conversation. As I mentioned, we need as many brains as possible to sort of think our way out of this.
Right, right. And I want to circle back to something else that pivot off something else you said before. You have a certain interest right now in microclimates. Maybe you can explain that a little bit because microclimates do actually affect everyone at their local scale, and that's something that Carson and I are certainly interested in understanding.
Yeah, I mean, this is a brand new area in ocean science, I think, and it's, as our instruments have gotten better and we've been able to really look at this range of variability in different places and locations, it's shocking how much variability there are in time space scales. And again, if we really want to think about what's going to influence that individual sea star or your individual salmon stock, we really need to understand the conditions that they're impacted by. And in the past, we've collected data that, once a year that was 100 kilometers apart, for example. And that tells us something about, interannual and interdecadal changes, but it doesn't actually tell us what influences different animals at the scales that they care about. And so
Right.
moving into microclimate research, I think, is really important. And thinking about the ocean as a microclimate. Um, and, people that are divers or that are surfers or that spend a lot of time in the water, they know this. They know that, on this side of that headland, it's going to be warmer than on that side of the
Hmm.
headland. But ocean science hasn't quite caught up with that yet. And so, for example, like at Hakai, we've got a fleet of the tidbit temperature sensors. So we can start really looking at these spatial scales. But those are often only at one depth, and the vertical scales are also really profound. Like we have one thermistor string that's about in water that's 70 meters deep, and we've got about 15 different sensors on there.
Wow.
And we've learned that the
It's an
bottom,
expensive string.
it's
Yeah,
not too bad. Yeah.
that's the work that got us involved in this whole process of citizen science was putting hobo temperature loggers and light loggers on a buoy string down in Little Cayman and seeing that there was a lot of difference in from one layer to the next.
Yep.
Yeah. Yeah, no, it's so interesting. I mean, you can see where the tide influences the water, you can see where the sun influences the water, and that there are these really profound layers that are influenced by those different processes. And you can start thinking like, I don't know, a fish at that point. Like, if I need to stay in water that's colder than 8 degrees, like the ulacan, which is another really important north coast species or northwest coast species, then I need to stay in waters that's this deep. But if there's not enough oxygen, then I'm kind of screwed. So you can really start thinking about again those multiple stressors.
Yeah, really, really interesting. I I, I want to go back to something about connecting people. I know that you're involved with a film festival. Maybe you can tell us about that because that is a good way to connect people.
Yeah, I mean, this is a brand new initiative, and it's been really exciting. Yeah, I have a friend who is a filmmaker, and we've talked at length about how frustrated I am that you do all this work, and maybe 10 people will read your paper or something along those lines. And how much really interesting information there is in the scientific realm that really never makes it into the public knowledge. Maybe at best, 0.1% of all of the scientific work that's done currently makes it into our public knowledge realm. And as we know, instead, there's all this other kind of fake news that's out there. And so, we've been brainstorming ways about how we can just try and bring scientists and filmmakers together so that if they work more collaboratively, then they can, that knowledge exchange will come naturally. And so we've created the British Columbia Environmental Film Festival. And yeah, essentially the concept is that scientists and filmmakers um, are on equal footing here. And so, those collaborations and those discussions are going to happen. Some of the highlights that we plan to have is almost like a discussion about the film's scientific credibility in a sense. We can, we're not going to necessarily start making films right now with filmmakers, but the films that we're going to screen, we're going to give some scientific feedback to the filmmakers so that that they again are part of that discussion as well. And yeah, we're hoping, down the line, it will lead to a more active sort of, working involvement between scientists and filmmakers.
I think that's just fantastic and a great place to end today. I want to thank you both, Dr. Kostchan, again for joining us, but Dr. Jennifer Jackson from the Hakai Institute, thank you for your time today. And if anyone wants to know more about the Hakai Institute, it's www.hakai.org, I believe. And the film festival, can they look that up somewhere?
Sure, yeah, it's www.bceff.org.
Perfect. Thank you, guys. It's been great today. Hopefully, we'll have you back again in the future and you can tell us something new.
Thank you.
Thank you, guys.
Thank you.
Okay, Carson, let's switch gears to the news. And for those of you that are joining us for the first time, we do have a newsletter that goes out once a week. And therein, we like to add 2 or 3 interesting articles that we've found from the news cycle that are climate related, and add into that an interesting scientific report and any other relevant information that we'd like to share for that week. And we send that out to you once a week, just the facts. And so please go ahead to 2degreec.org and sign up for the newsletter. Carson, in the news cycle this week, I've noticed that there was an article that was quite interesting and has the headline, "To understand how warming is driving harmful algal blooms, look to regional patterns, not global trends." What's going on there?
That's a really interesting article that's popped up, and it really highlights that even though there's a strong global climate change signal in seeing increasing algal blooms throughout the world, it's really in just certain places. Other places are seeing actually a decrease in harmful algal blooms, or just algal blooms in general. Some are not so harmful, but worldwide there are places where they're just not as prevalent as before, and it really highlights the fact that there are localized effects that are exacerbating these blooms, such as nutrient runoffs and hypoxic zones, and water circulation in the near shore that are very, very much localized. And to understand these, we really need to see a lot more monitoring taking place. And a lot of this monitoring is coming from citizen scientists out there who care about water quality and such. They're taking samples for science. And so we definitely need more of that going on at regional and local scales, especially in areas where these blooms are becoming more prevalent. But as well as places where they're not. I mean, we're looking at places right now like the coast of Florida, the
red tide,
sargassum in the Caribbean, the Turkish sea snot that's taking place right now around the coast of Turkey, and these are all places where we need far more monitoring going on, and that's something that is underscored in the article.
Yeah, I have seen in the Caribbean, especially the beaches that are on the windward side of the islands, do take on a tremendous amount of sargassum that's washing up on the beaches that needs to be cleaned. And Florida, obviously, with the red tide affecting local species quite greatly, being that particular one is toxic. Great. We'll watch that one. Switching gears again, let's look at the next one I wanted to talk about. This one is interesting. It says Earth is trapping unprecedented amount of heat coming from NASA. What's going on there?
As we touched on earlier in the podcast, this is a recent study that's come out of NASA with co-authorship with NOAA, where they took a look at the amount of heat that's being trapped in the atmosphere relative to what was projected by a lot of the global climate change models back in around 2013 or so, and they're finding that in many cases the amount of heat being trapped in the atmosphere is almost double what had been anticipated or expected by this time in 2021 and such. So that really is very significant in terms of raising alarm bells that the models that had been used in the last IPCC assessment report may actually be underestimating the magnitude of climate change and global warming across the planet. And the new generation of models that are being prepared right now hopefully they will be accounting for those and give us a much more reliable and accurate estimation.
Now, you're referring to the models. You're referring to the RCP values. Is that correct?
That's correct. The couple climate models, the global climate models that are being used by the IPCC in their assessment reports to look at how climate is changing and has changed in the past and is changing in the future. And there are approximately 40 of those models out there that they combine to get an estimate at different amounts of concentration of greenhouse gases in the atmosphere, which determine how much solar radiation is being trapped.
And so you're saying that this report is saying that we're, in some instances, exceeding the highest value models that they had.
That's correct. Yes, they're even the highest emission scenarios are underestimating the amount of heat that's being trapped in the atmosphere.
Yeah, definitely cause for concern. Well, thank you, Carson. Thanks for today. And to those listening, we will see you again for another episode of the 2 Degrees C Climate Chat. Thanks, guys.
Thanks a lot.
Thanks for listening to today's episode of the 2 Degrees C Climate Chat. If you have a question you would like answered, a topic for discussion, or would like to be a guest on the show, please leave a comment below. We'd love to hear your stories and climate journeys, and if you like what you've heard today, please like, subscribe, and comment wherever you hear your podcasts. Next week, we'll be joined by Jason Boyer, Chief Meteorologist for ABC News 13, to discuss his role in the climate conversation and that of those in broadcast media. So be sure to check back in then, or find out more about the stories you just heard by visiting our blog at 2degreesc.org and connect to others like you via our social media. Thank you to our sponsors and partners without which this podcast is not possible, with special thanks to Seren Media for producing today's episode. To find out more about our partners, please visit our website. And if you'd like to become a sponsor or partner, please email us at podcast@2degreesc.org.